Sometimes the biggest ideas come in the smallest packages. What if I told you a single page, just one page, from 1949 completely rewired how we think about, well, everything, from economics to evolution? That's exactly what we're digging into today.
Okay, so let me ask you this. How do you make the best choice when what you get depends entirely on what everyone else chooses to do? I mean, think about it. You're driving in traffic, you're trying to negotiate a salary, or heck, even just picking a checkout line at the grocery store. Your best move always depends on what other people are going to do. This is a huge puzzle, right? And it's one that's stumped the experts for a long, long time.
And the answer to that massive puzzle? It came in a paper so ridiculously short. It wasn't really a deep dive thesis. It was more like a birth announcement for a truly revolutionary idea.
And here's the title: Equilibrium Points in N-Person Games. Yeah, I know. Doesn't sound too exciting, does it? No flashy headline, just a super academic description. But when this thing was published, it landed like a quiet thunderclap.
And get this, the core proof, the entire revolutionary concept, was laid out in just over one single page. Can you believe that? It's a total masterclass in getting straight to the point.
So, who was the genius behind this? A young Princeton math student named John Nash. We're talking about a brilliant, kind of eccentric grad student who at just 21 years old wasn't just solving some old problem. No, he was literally creating a new lens to see the entire world.
All right, so what was this earth-shattering idea? Nash himself called it an equilibrium point, but honestly, there's a much better way to think about it. Just call it the point of no regrets. Okay, so to get this, we first have to understand the playing field Nash set up. He talks about an N-person game, and that doesn't just mean poker or chess. It's any situation with multiple people, that's the N, where everyone has a set number of moves they can make, or strategies.
Now, inside this game, what's your goal? It's to find what Nash called your countering strategy, which is really just a fancy way of saying it's your best possible move, the one that gets you the best result, based on what you think everyone else is about to do.
And that right there leads us to the big idea, the equilibrium point. So picture this. It's that one special, stable outcome where every single person in the game is playing their absolute best move at the exact same time. It's the point where everyone is countering everyone else perfectly. Yeah, the technical term is a self-countering N-tuple, but don't worry about that.
Because here's what that really means. In plain English, it's a situation where, after everything is said and done, nobody wishes they'd done something different. You look at what everyone else did, you look at your own choice, and you think, yep, given their moves, I made the best call I could. There's no reason to change your mind. You have no regrets. Okay, I know that can still sound a little abstract, so let's make it super concrete. Let's play a little game.
All right, check this out. We've got two players. You can be player A. They can either choose to collaborate or to compete. The numbers you see are what they get, their payoffs. So for instance, if you collaborate but the other player competes, you get nothing, and they walk away with a big score of 5. Now you can see that the best outcome for the group is if you both collaborate, right? You both get 3 points. So, what do you do?
So let's think this through. As player A, you reason it out like this. Okay, if player B collaborates, what's my best move? Well, I should compete, because getting 5 points is way better than 3. All right, but what if B competes? Well, then I should still compete, because getting 1 point is better than getting 0. See, no matter what the other person does, your best move is always to compete. And here's the kicker. Player B is doing the exact same math, which leads us to this kind of mind-blowing conclusion. The only stable outcome, the only point of no regrets, is for both of you to compete. You're both locked into a choice that's actually worse for both of you overall, but neither of you can do better by changing your mind alone.
Okay, so finding that stable point in a simple little two-person game is one thing. But this is where Nash's real genius just explodes onto the scene. He proved that for any game, with any finite number of players and strategies, one of these equilibrium points has to exist. It's guaranteed. And how he did it? Well, it's just amazing.
I mean, the problem he was facing was huge. And to solve it, he reached into a totally different field of math, something called topology, and grabbed this tool called Kakutani's fixed point theorem. This was a completely unexpected, brilliant leap of thinking.
And you can actually understand this theorem with a really cool analogy. Imagine you have a paper map of, say, your country. Now, take that map, crumple it all up into a ball,
don't rip it, and just drop that crumpled ball anywhere on top of an identical, flat copy of the same map. Kakutani's theorem guarantees that there will be at least one point, one tiny spot on that crumpled map that is sitting directly above the exact same spot on the flat map below it. That's the fixed point.
And this is the light bulb moment for Nash. He realized that the set of all possible strategies in a game, that's the map. And the process of every player trying to find their best response to everyone else, that's the crumpling of the map. So the Nash equilibrium is that fixed point. It's that one guaranteed spot where all the choices, all the strategies perfectly line up. It proved that a stable outcome always has to exist.
The proof is beautiful, for sure, but the implications of that proof, that's what changed everything. That's what remapped the world.
You have to remember, before Nash came along, game theory was mostly stuck on two-person zero-sum games. Think poker or chess, right? Situations where, for me to win, you have to lose. But that's not how most of real life works, is it?
Nash he blew the doors wide open. His proof worked for any number of players and for games where everybody could win or everybody could lose. All of a sudden, we had this powerful mathematical tool to find the stable points in, well, everything. We're talking Cold War arms races, how to design auctions, how animals compete for survival, even how traffic flows through a city. It gave us a brand new language to talk about strategy.
So in the end, that one little page of math gave us a totally new way to see the hidden logic of our world. It helps us spot those stable, no-regret situations that are popping up all around us, all the time. So, now that you know what it is, where do you see it?